Assalamualaikum warahmatullahi wabarakatuh and good day. Okay, see me again in Thermodynamics classes. Okay, we continue the lecture today for the new topic. That is topic chapter number 6. Okay, this topic is about the thermal power plant. Okay, thermal power plant. Okay, what will be covered in this chapter is basically you will learn about gas turbine engine and also the gas uh, vapor power cycle that means based on the Rankine cycle. Okay, actually, power when we talk about power plant, uh, what it mean of the power plant? Okay, actually, the power plant station is a power plant in which heat energy is converted to electrical power. That's when from mechanical uh, heat energy that come from mechanical, then we convert it to the electrical power. Most of the power stations contain one or more generators. That means rotating machines that convert mechanical power to electrical power. So there are various of the power plant. Uh, Number one is gas turbine power plant. You also got the steam turbine power plant, nuclear power plant, hydroelectric power plant, solar power plant, geothermal power plants, tidal power plants, and wind power plant. Okay. Uh, what it means by gas turbine power plant? This is a power plant that use a gas as a working fluid. Okay. And what about steam turbine power plant? Okay, this is a power plant that use vapor or use liquid to convert it as a working to convert it to the energy. Okay, but in this chapter, we are also we only study cover on the gas power plant and steam power plant. Okay, gas turbine engine. Firstly, we look on gas turbine engine. Actually, gas turbine engine. Uh, Many of you have seen this engine. It is coupled to the aeroplane or to the aircraft. Okay, it is a power production and generating thrust for the jet propulsion. So, gas turbine engine has a great, actually, it has a great power to weight ratio compared to the reciprocating engine. This is the advantage of gas turbine engine. But the disadvantage of this gas turbine engine, when we compare to the reciprocating engine, it has uh, when we compare to reciprocating engine, reciprocating is a small size, but gas turbine engine have a big size and they are so expensive for this turbine engine. Why? Because they have a high speed and high operating temperature. Designing, manufacturing gas turbine. So for the engineering and material standpoint, it is much expensive because we want to. It require a high operating temperature. Okay. It also tend to use more fuel when idling. So they prefer a greater rate, the constant rather than the rotation load. Okay. Basically, the gas turbine engine have a compressor that means in front of the combustion chamber, and after the combustion chamber, it have a turbine. So this is a main principle or main work of the gas turbine engine. Okay, it have turbine, compressor. Okay, in front of the compressor, it have a intake port. Okay, and at the end of this engine has an exhaust port. Okay, okay. How this principle of gas turbine operate? Actually, it operate based on the combustion of the fuel and air. So this gas engine derives their power from burning fuel in the combustion chamber in here, and it produce a high energy power that turn this turbine and make it as a thrust force to this engine. So it will push all the flow, all the energy, and this engine have its energy. Okay, actually, to operate this combustion in the combustion chamber, you have to turn firstly the compressor. Okay, when the compressor turn, it will suck the air from in front of the engine to the compressor, and then it goes to the combustion chamber. It will turn the turbine, and then the turbine automatically will create a thrust and also uh, rotate the compressor in front of the combustion chamber. So it helps to make it as energy. So this is a schematic diagram of the gas turbine. So you have you can see this is a compressor, and then combustion chamber, and also the turbine. So in between compressor and turbine, there is a long shaft. When the turbine rotating, so the compressor will rotate as well to suck the air from atmosphere. Okay, this picture is called an open cycle gas turbine engine. Why? Because it, the cycle is not connected. Okay, this is the cycle is not connected. So what happens? In front here is the atmosphere, and here is the atmosphere. So it is not connected. So we call it open cycle. Okay, the ideal when we want to analyze the gas turbine engine, so the ideal cycle that we use is a Brayton cycle, or called Brayton cycle. This is the ideal cycle and also called as a Joule cycle. Okay, it is a standard air standard ideal cycle for gas turbine engine. So in this, basically, Brayton cycle have four processes. This is the analysis for the thermodynamics. So process number one is isentropic compression. Is in the compressor. Process number two is constant pressure heat addition. Uh, this is at the combustion chamber. Process number three is isentropic expansion in the turbine, and process number four is constant pressure heat reduction. Okay, this is a TS diagram and PV diagram. So you have to remember this graph for the gas turbine engine. Okay, four processes, one and two. Process number one, two and three is heat addition. Uh, three, three and four is power process. That means combustion chamber. So four and one is exhaust or heat rejection. Okay, this is what I said just now. This is a closed cycle because it had a heat exchanger, so the cycle is continuously loop one cycle. So when it look like this, we call it as a gas closed cycle. Okay, this is the formulas that can be used for the calculations or analysis of the Brayton cycle. So for process number one, that's mean process one and two, state one and state two is called isentropic expansions. So when you see as isentropic compression, so you have to use or you can use the three relationship of the equations. That means pressure, volume, and temperature. So at process number two is two and three. This is the constant pressure heat addition. So in here, what happened? We only have Q in, okay, for that process. So you use the closed system. Q minus W is equal to delta U. So simplify that equations, then you will get these equations for heat addition in that process. Process number three, that means point 3 to 2.4 is isentropic expansion. Also can use the equation relationship equation isentropics. And process number four is constant pressure heat rejection. So Q out as same as process number two. So you get this equation. So the thermal efficiency based on the thermal cycles, that means the basic cycle W net over the Q in. So you simplify or derive these questions, then we will get this is the equations output for thermal efficiency for Brayton cycle. So in these equations, the simplify RP, that's mean pressure ratio has been introduced. This in RP is a pressure 2 over pressure 1 or pressure after over with the pressure initial. That means not 2 and 1. It also can use 4 and 3 or 6 and 5 or so on. Okay, the theoretical analysis for thermal efficiency in the Brayton cycle, as you see in the graph, thermal efficiency compared to the pressure ratio. What happens when the pressure ratio is increased? That means we have a greater power thermal efficiency until it comes at 20 pressure ratio or 25. Then this graph will be horizontal. Okay, that means when you put 30 pressure ratio, that means it's not enough pressure to increase the thermal efficiency. Okay, the graph is only curve. Part of that, uh, you also have to know another point of work back work ratio. Okay, another point of term in thermodynamics in Brayton cycle is back work ratio. What is a back work ratio? Back work ratio actually the work that's come the work from the compressor divided by the work from turbine. Okay, because you know when the work from the turbine get the power from the combustion chamber, not all this power is converted to the energy. Okay, there was a few energy that goes back to the work compressor, and this energy work to the sun we can find or um, we can turn required as work input. Okay, and it can be show as a backward ratio. So the backward ratio, as I mentioned, work compressor over work turbine. So using the equations for work compressor and also work turbine, so you will get the equations, and to calculate this backward ratio, just use the temperature between all the points in the cycle. Okay, let's go for the let's go or look for the example. Okay, in here in this example, it said the ideal air Brayton cycle. Okay, the ideal air standard Brayton cycle operates in air with air entering the compressor at 25 kilopascal, 22 Celsius. The pressure ratio, that's mean RP, is 6.6 over 1, and the air leaves the heat addition process at 100 Kelvin. Determine the compression ratio and the turbine work per unit mass flow, the cycle efficiency, and the bed work ratio. Okay? Assume constant specific heat at room temperature. Okay, this is it's still at room temperature. You can also use the table in A17 to use because it state that the constant specific heat at room temperature. But I like you to do the analysis based on the calculation. Okay, this is the air standards ideal. That means this cycle use air. When it use air, what I have told you that you have to use the equations to make this analysis, or you have to assume this is the air standard cycle, so use it as the ideal gas approach to do this analysis. So this is a TS diagram for this Brayton cycle. Okay, there was four processes here. So firstly, by applying the conservation energy for steady flow, and you also neglect changes in kinetic and potential energy to process one to for the compressor. So the compressor is isotropic. So then we get the formula, uh, the total energy in is equal to total energy out. So simplify this equations to get this. And you also know the conservation of mass. That means give m dot in is equals to m dot out. So that means all mass flow rate in this cycle is equal. Okay. So based on the work compressor, that means at process number one, that means state one and two, the work compressor can be used uh, can be used these equations. So you must to find T2 and T1. Okay, to find this T, temperature 2, temperature 1 has been given, I think. So you use, this is the first, this is the first process, 1 and 2. Okay, so 1 and 2 is isentropic because we assume that the compressor and turbine, compressor is isentropic, and also turbine is isentropic. So you can use the relationship of isentropy equations. So using these equations, then you will get T2. Okay, put it T2 in the equation work compressor, then you get the answer of work compressor in term of unit joule per kilogram, small w. Okay, for process 3, 4, for process 3, 4, 3, 4, also for the turbine, same as the equations, but it refer to the turbine. So you have to find T4 or T3. So this is a isentropic process. So using the relationship of the temperature and pressure for the isentropic process, so you will get the answer of T4, and then using this value of T4, you will get work turbine. Okay, so we go back for the process 2, 3. 2, 3, we know that the mass flow rate is equal. So from there, Q in, uh, Q in based on the equations uh, regarding with the closed system, Q minus W is equal to delta U. So then you get these equations, put in the value, and then you have the amount of Q in. Okay. So the net work W net is equals to W turbine minus W uh, compressor. So the value after you put all the values turbine work turbine and compressor, you will get work net. And the thermal efficiency based on the equation W net equals to Q in. So put all the values in the equations for thermal efficiency, then it will give you 40% of the efficiency for this cycle. Okay, and also if you want to if you have to find a backward ratio, also use the equations, and then from there you have the values, then it gives it 0.448. Okay. Okay, another one is derivations of actual gas turbine from ideal ones. Okay, what I have told you just now, it Brayton cycle is based on the ideal. That means on the theory of the Brayton cycle. Okay, but in reality, when you want to make the calculation or analysis, you cannot based on the theory or the on the ideal. So you if you have to calculate based on the actual. So when the actual process, that means we have learned in chapter number 4, I think, on the isentropic efficiency of the compressor and also the turbine. The equations is based on the, the efficiency of the compressor is Ws over W actual. That means W ideal, work ideal over work actual. Okay, find work ideal and work actual from these equations. You will get the efficiency of compressor. It's also like the turbine. Okay, so this is a TS diagram. What I have said just now. That means straight line. The straight line is ideal. The dot line is actual. Okay. Okay, this is straight line and this is the actual process. Okay. Okay, we look on the example. Okay, when and how you have to do this analysis based on the equation, based on the question. Okay, look at sample problem 6.2. It gives a simple Brayton cycle use air as a working fluid. Okay, as a pro, uh, as a pressure ratio of 10. The minimum and maximum temperature in the cycles are 295 and 1240 Kelvin. Let's see the next sentence. It says, assuming an isentropic efficiency of 83% of the compressor and 87% of the turbine, and using constant specific heat at room temperature, determine A, B, and C. So in this equation, in this case, it said it have a actual it have an actual value because it have given in the sentences that the third sentences that the isentropic efficiency has been mentioned. So when you see this sentence, that means you have to do the calculation based on the actual value. Okay, to do this, let's go to the equation link here. This is a solution for this problem 6.2. Okay, the solutions is this. Okay, firstly we draw PV diagram and TS diagram. Okay, for the actual and the ideal. Then list down all the given data that has been given in the question, and then try, or you must find each value of the temperature in the graph. From here, temperature 2 has been find the value. Temperature 4 has been find based on what I have teach you how to find when the process is isentropic. So you can use the relationship of the equation, isentropic equation. And then from there, you know the compression efficiency is based on these equations. So you will get the actual value T21. Okay, we took T21 actual or ideal. T21. This is the actual. Okay, T2 actual value. So this is the value of T2 actual, and next find based on the efficiency of the turbine. So you will get the temperature actual for temperature number 4. This is actual. So based on these actual values, uh, A, it want you to find work net. So from work net, use a equations work turbine minus work compressor. But in these equations, don't put the ideal value of T4. Okay, you have to put the actual value. Why? Because the question have give you the efficiency of the turbine and compressor. So you have to put the actual value. So put it actual value in the equations, then lastly you will get the values of work net based on the actual value of temperature in 4 and temperature in at 2. Okay, same as B, thermal efficiency. Okay, thermal efficiency, work net over Q in. So Q in T3 minus T2 prime. T2 prime is actual. Okay, so you put here also the actual value, and then you will get the actual efficiency value of that uh, analysis for Brayton cycle. Okay, so it how it is how you analysis the question based on the actual value. Okay, when it gives in the equation. Okay, next we go to development of gas turbine. Okay, as I said just now, gas turbine, the idea cycle to analysis based on a gas turbine is Brayton cycle or Joule cycle. Okay, but this gas turbine engine or gas turbine power plant is so expensive, so difficult to make yourself, uh, and it has some advantage and disadvantage. So it have a possible way to improve the cycle. Okay. The first one is the ideal cycle, but when you want to improve this gas turbine cycle or Brayton cycle, number one, you can increasing the turbine inlet or firing temperature, because gas turbine, the combustion chamber itself can sustain with a high temperature. So to make it more powerful, you can increase the turbine inlet or firing temperature. Number two, you can also increasing the efficiency of turbo machinery component uh, turbine and compressor. So it maybe depends on the material how you want to design that turbine and compressor to make it sustainable with a high temperature. And number three, do some addition modifications based on the basic cycle, uh, modified based it on the intercooling, or you put it in the basic cycle intercooling, regeneration or recuperations, and also reheating. Okay, that is three modifications uh, can be added in the basic cycle. So in next, we will see or learn, and also you will be introduced this Brayton cycle based on the concept of modification based on the intercooling, regenerations, and also reheating. Okay, that's all for today. That's all, not for today. That's all for this time. See you in next uh, class or next um, meet. Okay, thank you very much and assalamu alaikum. Have a good day.